Hello and welcome to the PSE demonstration video. In this demonstration, we will build the model of a small mast and analyze it. The first thing to do is to select from the General Options menu the 3D option. Then we will ensure that the selected design code is correct for the need of this tutorial. The software supports the ASD89 and the ASD10. We can define the design code from the Design Code option menu. This example will use the ASD89 code. To modify the unit system, we will click on that icon. We will use the imperial system with the length in feet. There are multiple ways to create the structure elements such as joints and the members. In this example, we will use the grid technique. We will specify a given spacing between the lines in the X direction and in the Y direction. The spacing in the X direction will be 7 feet and the spacing in the Y direction will be 3 feet. The grid orientation will be in the XZ plane. To create the base of the mast, we will apply the joints on the attached points of the grid. To do so, we have to select the Add Joints command and select the grid attached points. We can then extrude these joints in the Y direction. To extrude the joints, we must first select them and use the Copy/Extrude command. There will be 2 extrusions spaced at 5 feet each for a total height of 10 feet. Now that the joints are created, let's add the members. To do so, we use the command Add Members and define their position. We will add the diagonals, the horizontal, and the vertical members. It is important to note that these members are not subdivided at this point. We will have to use the Attach Crossing Members command to create a joint at the intersecting point. After, we select the whole structure and use the Copy command. We will copy this part of the structure 3 extra times. The information needed to copy the structure is the height of the item to be copied. In this case, the height is 10 feet. We will then add 3 different surfaces to simulate the wind walls. To make sure that the 3 different surfaces are recognized by the software as one wind wall, we have to create a group containing those 3 surfaces. To do so, we have to go into the Tables, Wind Walls API 4F, and define the category and surface group. In this example, it is a 3-sided wind wall. The wind wall can be much more complex than that, but for the purposes of this example, we will use a simple 3-sided wind wall. The surface group can contain as many surfaces as needed. We will now assign the support conditions to the base joints. After that step, we will assign the sections of the columns. A fast way to select the column is to select them from the top of the structure so that all columns are selected at the same time. To attribute sections to the columns, we will use the Members Attributes command and add the new standard section. We use the American Section Library. Let's select a square HSS as the section type. It will be a 4 by 4 by quarter square HSS. Now that the section has been added, we have to attribute the section to the selected columns. I will then dim the selected columns to easily select the rest of the structure. We will then select the horizontal members by going into the Special Select command. In that command, we will then specify the section of the members in the XZ plane only. After the selection of these horizontal members, we will attribute them a section by going into the Member Attributes command. We will use a 6 by 4 by 3/16 rectangular HSS. Make sure to use the correct material. I will also correct the material of the columns. To do so, we can go into the section properties and change the material. We can see that the two sections use the same material. Regarding the rectangular HSS, we will add a rotation of 90 degrees to make sure the long side is horizontal. Again, we will dim the selected members and all the remaining members will have the same section, which would be a square of 3 by 3 by 3/16 HSS. After, we can use the Verify Input Data command to verify if everything is correct so far. If everything seems good, we now need to apply the loads to define the loads combinations. Here, we will add the three different basic loads such as the dead load, the hook load, and wind loads. There will be multiple basic wind loads for multiple wind orientations. To generate the text quickly, we will use the increment field command. This would be the prefix, and this would also be the closing suffix. We will increment the orientation by 45 degrees. So here it would be the wind load. This as the live load, and this as the dead load. We will then create the load combinations. To make this fast, I will use the wizard corresponding to the ASC705. This would not directly correspond to the API 4F requirements, but I will use the edit command to make the modifications. We will add the hook load to the combinations number 2 and 3. We will then repeat the field with Ctrl B. We will use an AMOD of 1.33, so we're using the ASD89 code. We will also suppose that the hook load is always active, except for this case. We have all zeros everywhere, and to facilitate the viewing of the combination, we can also use the hide zeros command. All of the load combinations are now completed. If needed, you can also use the copy-paste from Excel directly in the table. Now, let's add the self-weight of the structure. The self-weight will be applied as the dead load in the -1 Y direction. The self-weight is displayed here. For this example, the hook load will be 200 kips. To simplify this video, the hook load will be distributed to the 4 joints here. To add the load, we select the 4 joints. We go into the Joint Load command, enter -50 kips in the Y direction, and add it to the structure. We will now add the wind loads on the structure. We will apply the wind loads on the members first. To add a wind load on a member, we go into the Member Load command and go into the Wind Loads tab. We will define the 80 miles per hour at 0 degrees basic load and define the wind profile. We will suppose the ground position is -20 feet below the base joints here. Let's specify a wind velocity of 80 miles per hour. We will then automatically generate the other wind load profiles for each wind direction. We now have all the wind profiles in the different wind directions. Then, we will assign the profiles one at a time to the members. So we have here wind according to the X direction, and then we will assign it to every other 45 degrees direction. So every load will be assigned and associated with the basic load. We can now see that every member has been loaded, and if we look closer, every member has arrows around it representing the wind direction. Members without these arrows do not have wind loads on them. We will now add the loads on the 3 surfaces. We will select the 3 surfaces, dim the rest of the structure, and go into the Add Surface Loads command. We will have to repeat the same process to apply the wind loads. Because those surfaces are part of a wind wall, they will have the same wind shape coefficients according to the API 4F standard for 3-sided wind wall. All shape coefficients will be automatically calculated. Let's select the correct basic load to the correct wind profile. Now we can see that the wind is also applied on these surfaces. If we want to see the shape coefficients for those members, we would go into the same menu where we applied the loads and open the table. we can see that each surface has its corresponding shape coefficient according to the wind direction and its positioning in the space. If we select a different wind direction, shape coefficients are also different. All of the first columns of the table are input, and the last columns are for verification. Those columns are already computed for the user. If you make modifications to the structure, they will be automatically updated. We can now hide the loads since all the loads have been applied to the structure. We can go to the Display Options menu. You can also display one load at a time so you can verify the loads separately. We can now verify again if we miss something in the input data command. If everything checks out, we can launch an analysis. We will start with a static linear analysis. After the completion of the analysis, multiple results are available by going into that menu. We can begin by showing the displacements of the structure. The displacements you can see here correspond to the selected load combination. Here, it was only the dead load. If we had the hook load, we can also see the displacements by changing the view of the structure. If we add a third load combination with the wind according to the X direction, we can see the movement of the structure as an effect of the wind. We could also display the axial load. To modify the scale, we can go into the Display Options menu, go into Scales, and define a new ratio for the axial loads. We can also hide the text. The next step would be to verify the resistance of the member according to the ASD 89 code. To do so, we first have to assign the additional parameters required to correctly design the structure. By double-clicking on any member structure, we can access the Steel tab. In that tab, we can specify the unbraced length and the bending or compression. Nothing has been specified yet. When everything is 0, the software considers that they are supported at their ends. So, a small member like this would be supported here, but in reality, it is not really supported there. To be conservative, we will use the total length of a diagonal as the unsupported length. The software can automatically calculate the unbraced length by going into the Edit and then Recalculate to check all of these options. To correctly calculate the bucking length of the member, we will check this case. If I'm going back to the member, we can see the updated values. In this example, if we look at the front members, because there is no lateral support from top to bottom, the software measures the bucking length as the total height of the structure. This would be too conservative because the horizontal members provide some sort of lateral support. Because those supports are not fully efficient, we will assume the bucking length as twice the height of the member, which would be 10 feet. Every designer should do his own assumptions regarding the design of his structure. Now that the steel parameters have been set, We are now ready to run the steel verification. We will also perform a nonlinear analysis to see the performance of the structure. By checking this case, we can have a quick look at the ultimate limit states regarding every load combination. As we can see, the color schemes are described at the bottom right of the screen. Red members would have a unity check higher than 1, failing regarding their ultimate limit state. In this model, every members are within the ultimate limit states. If we want to see the most stressed members, we can go into that menu and then specify a minimum unit value to only display the members having an ultimate limit state higher than that value. By doing that, we can quickly see the most stressed members of the structure. We will reset it to 0. The member verification results can be looked at in detail. If we select this member, for example, we will look into the tables and choose the ultimate limit state summary for the selected member regarding all or specific load combinations. By sorting the column, we can see which load combination is predominant on that member. Then, we can see that the compression has the biggest effect on that member with bending. The maximum limit states that governs it is the compression. To obtain more information on that limit state, we can go into the detailed tables here. We will look into the compression tables for the selected member. In that table, we can find more information such as the unbraced length, the ratio of gyrations, resistance on both strong and weak axis, the allowable stress, the resistance, and the actual stress. We can then have an overview of the compression limit state results. You can also see more detailed results here if any of the limit states have to be more detailed. There is also another option that consists of viewing the ultimate limit states within the members. To make that option available, we have to go into that menu and select the option Limit States Calculation at each division and launch a new analysis. Now, we can see the ultimate limit states variation within the physical member to find the maximum. In that case, it is the top of the physical member. The physical member is composed of member number 21 and number 22. Let's look at the deflection of one particular load combination. With the side view, we have an overview of the structure displacement. If we include the P-delta effects on the structure, we can notice differences on the structure displacements and the member's resistance. If we look back at the ultimate limit state, we can see that the results have included the P-delta effects. I hope you enjoyed this video. For more videos and information, please visit our website at www.safi.com.